Welcome to Networks Professionals.
All right, let's jump right into this explainer and figure out how the massive, honestly kind of mind-boggling world of modern IPv6 networks actually stays organized. I mean, we're talking about an ecosystem built to handle 340 undecillion potential addresses. That is a number so staggeringly huge, it's literally hard to wrap your head around. And yet, somehow, whenever you connect a device, the whole system just flows.
It's a massive challenge when you really stop to think about it. Just imagine the absolute sheer chaos if this didn't work smoothly. Every single time you plugged in a laptop, a smartphone, or, I don't know, your smart thermostat, you'd be risking IP collisions, routing failures, basically a total blackout of connectivity. So how do these millions of devices seamlessly find their exact place on an IPv6 network without stepping all over each other? Well, the answer lies in an invisible network concierge working tirelessly behind the scenes. We absolutely need a system that expertly directs traffic, hands out the digital keys, and makes sure everyone has exactly what they need to communicate flawlessly.
And that concierge? That's DHCPv6. It's our ultimate organizer. Simply put, DHCPv6 is the protocol used to automatically assign, renew, and reclaim IPv6 addresses. But, its role goes way beyond just handing out a raw IP address. It gives you centralized control over your network and distributes critical configurations like pointing your devices to the correct DNS servers. Because, let's be real, a perfectly assigned IP address is completely useless if your machine can't resolve web addresses to actually reach the internet, right? DHCPv6 is the architect keeping that chaos at bay.
So, here's our roadmap for this explainer. First, we'll meet the IPv6 manager. 2, we'll compare stateful versus stateless assignment. 3, we'll decode the identity badges. And finally, 4, we'll walk through the actual message exchange process.
Okay, let's kick things off with Section 1. Meet the IPv6 manager and take a look at centralized control.
Let's start with a macro view of the protocol's core responsibilities and how it acts as the centralized brain of the network. DHCPv6 does so much more than just issue single addresses. It manages the entire lifecycle. It assigns an address when a device joins, renews it if the device sticks around, and, this is crucial, reclaims that address when the device leaves. Think about a busy downtown coffee shop, right? Hundreds of devices are connecting and disconnecting every single hour. Without actively reclaiming those addresses, you risk total resource exhaustion. Plus, DHCPv6 handles something called hierarchical prefix delegation, which we'll get into in just a bit, and it pushes out those vital network parameters to keep connectivity totally frictionless for the end user.
Moving right along to Section 2, Stateful versus Stateless Assignment. Let's look at the assignment modes.
Now, this is a really vital distinction in modern networking, and it's all triggered by router advertisement, or RA, flag settings. We've got stateful DHCPv6 on one side and stateless on the other. Think of stateful DHCPv6 like a full-service hotel concierge handing you the exact specific key to your room. The server strictly manages your entire IPv6 address and keeps a perfect, meticulous ledger of who has what. Network architects absolutely love this for highly controlled enterprise environments where auditing and tracking are non-negotiable. Stateless DHCPv6, on the other hand, well, that's more like being given a map to find your own room, while the concierge just casually points out where the pool is. Clients configure their own addresses using SLAAC, which is brilliant for lightweight, massive-scale mobile and IoT networks. But here's the catch. Those devices still reach out to the DHCPv6 server just to fetch supplementary info, like those crucial DNS IPs.
All right, let's get into Section 3, decoding the identity badges, and see how we move beyond traditional MAC addresses.
To really understand how these assignments work under the hood, we kind of have to cut through the alphabet soup. Let's start with IA_NA. The big takeaway here is that IA_NA is the exact tool used when handing out a single, specific address to a single connected device. It stands for Identity Association for Non-Temporary Addresses, and actually that word non-temporary is the key. If you're used to SLAAC privacy extensions, where devices constantly randomize their temporary IPv6 addresses to avoid tracking, well, IA_NA is the exact opposite. It's precision assignment right at the individual interface level, giving a specific network card a permanent, managed, non-temporary address.
Now contrast that with IAPD, or prefix delegation. This brilliantly illustrates just how scalable IPv6 is compared to the old days. Back in legacy IPv4, because of address scarcity, handing a home user an entire routed subnet was practically unthinkable. But with IAPD, an internet service provider can delegate entire subnets. We're talking massive /64 or even /56 blocks directly to the gateway router sitting in your living room. The ISP is basically saying, hey, here's a huge chunk of addresses, you manage everything inside your house. This exact mechanism is literally what makes modern home mesh networks and expansive smart homes possible. It allows hundreds of smart bulbs and appliances to route perfectly without ever needing your ISP to step in.
Now, if you're coming from the world of legacy IPv4 networks, you're going to want to just wipe the slate clean here. For decades, IT professionals relied heavily on MAC addresses, the physical hardware address of a network card, to lock down IP reservations. I mean, we all remember the good old days of managing those endless nightmare Excel spreadsheets full of 12-character MAC addresses, right? Well, you can say goodbye to that because DHCPv6 abandons MAC address reservations entirely.
Instead of MAC addresses, the protocol introduces this vastly superior two-part system, the DUID and the IAID. Let's break this down. Imagine your laptop. The laptop itself is assigned a DUID, or DHCP Unique Identifier. Think of it like the device's permanent global passport. But your laptop might have an Ethernet port, a Wi-Fi card, and maybe even a Thunderbolt dock. That is where the IAID, or Identity Association Identifier, comes into play. When you plug in an Ethernet cable at your desk, that specific port uses IAID number 1. When you undock and switch over to Wi-Fi, it uses IAID number 2. The server sees the exact same DUID, so it knows it's still you, just entering through a different door. It is an incredibly elegant solution.
Let's bring it all together in Section 4, the message exchange process, and look at the actual client-server dialogue.
The protocol really has two main ways of actually talking on the wire. The first is the two-message exchange. This is highly efficient, and it's triggered by a specific technical flag called the rapid commit option. You'll see this heavily used in high-performance networks, where there's only one authoritative DHCPv6 server and absolutely no need to shop around. It is a lightning-fast back-and-forth play. Step 1. The client sends a solicit message basically saying, "Hey, I need an address quickly." Step 2. The server immediately responds with a reply, allocating the address right then and there. Done and dusted in just 2 steps.
But in your standard, robust enterprise setups, where multiple DHCPv6 servers exist for redundancy, we use the 4-message exchange. If you've been around older networks, you probably remember the IPv4 DORA process. Discover, offer, request, acknowledge. Well, IPv6 evolved that into SARR, solicit, advertise, request, reply. First, the client sends a solicit out to the network. Second, multiple redundant servers hear this and reply with an advertise message, essentially competing to offer their configurations. Third, the client reviews those offers, selects one, and sends a formal request message specifically to that chosen server. And finally, in Step 4, that server sends a reply confirming the final allocation. So yeah, it's a slightly longer conversation, but it guarantees total accuracy across a complex, multi-server environment. When you really step back and look at how powerfully DHCPv6 manages infinite prefixes, dynamically tracks identities without relying on MAC addresses, and cleanly adapts its conversation based on network size, it truly is a marvel of engineering. But with billions of new IoT devices coming online every single year, it begs a pretty fascinating question. As our networks grow infinitely larger, will protocols like DHCPv6 eventually hand over control to self-configuring, completely stateless systems, or will we always need that centralized concierge keeping the peace? It's honestly the ultimate debate happening right now in network architecture. Thanks so much for joining me on this explainer, and keep questioning how
Thanks for watching.